Hello, Errichto here with problem and reachability from a recent Codeforces round. In this problem we are given an array of integers a(n) and we defined reachability. From x we can reach y if there is a series of jumps that we can make such that for each two consecutive numbers their end is greater than 0. What it means is that if given this sequence, like in the sample test 1, 3, 0 to 1, if we write them in binary form, then we can jump directly, for example, from first number to the second, because they have a common bit. This means that their end is greater than 0. This means we can jump like that. Then from 1, 1 we can jump to 1, 0, because this bit is common. And this means that 4 is reachable from index 1, even though their direct end is 0, but we can make a series of jumps. The problem is to answer a bunch of queries. In each query we are given two indices x, y, and we should say yes or no, or actually she or foo, whether y is reachable from x. Let's quickly see some ideas that will not work for this problem. One of them is to find kind of connected components of this graph of n vertices, where we see which pairs of vertices are connected directly with an edge, and this doesn't work because the graph is directed. Here from 1, 1 we can get to 1, 0 or to 0, 1, but we cannot move between 1, 0 and 0, 1. Remember that edge is directed from smaller index to greater index. Some other idea might be to do something greedily, like going to a number that has bigger number of bits that are turned on. There are just counterexamples against that. And of course we can't just do brute force for every query separately going through the sequence, because that would result in at least n times q. Now you can stop a video for a moment to think about a correct solution, and now let's solve this problem correctly. For each number we want to know which bits are on, what is possible in every language in some easy way. And then, if for every bit we know which numbers have this bit on, the same here for the second bit, this number, and this number, we know that for those green marked values and for blue ones, we can move to any next index. For example, from the first green we can move to this one and this one. For this green we can move to the last green, and so on. For every bit we have some group of indices between which we can jump, and the same for every bit. Let's see how it looks like on some bigger example. Here we have it, where each number we know with colors which bits are on, and we have up to 20, or actually 19, because this is the number of bits in numbers up to 300,000, which indices have this bit on, and thus we can jump between them. It would be nice for every vertex among those n vertices to know to which vertices we can get. Having that information we could answer queries quickly. And here, because of this special format, this will be possible. In general graph, for a vertex we would have to know to which of n vertices we can get, and that wouldn't fit even in the memory. Also time would be too slow. Here, for example, for vertex 2, this one, we know that we can jump to the next green, that is 3, and because here we also have blue, we can also jump to every next blue. So we can get to this 3, and because for something blue we can jump to every next blue, it means we can visit all other blues to the right. The same will be true for every color. For every position there is some suffix that we can visit. This is because if we can get to some vertex, like blue 3, then we can visit every next vertex in this group, because in particular there are edges from 3 to 4, from 4 to 7, and from 7 to 8. Those are indices. Indices that we gathered that have the same bit on. So information for a given vertex, here it was 2, for every bit, for each of those 19 vectors or lists, to which vertices I can get, this can be stored as 19 values. For each vector, some suffix will be possible to visit. We can combine this observation with dynamic programming to be able for every vertex to find those suffixes. We go from right to left, and if for some vertex we know which suffixes are reachable from this vertex, and some other vertex, we also know that, then we can combine that. And here with black I marked some suffixes. If some other vertex can get to, let's say, this suffix, and this suffix, and I have some new vertex from which I can directly jump to either that one that is marked with black suffixes or this one with purple suffixes, then his new suffixes that are reachable are the combination of those. Like for each suffix start I take the minimum, and I can visit everything here, and everything here. I can combine two vertices in O of 19, just taking minimum for all the suffixes. That might be not clear right now, but we will explain that again looking at the code. My implementation you can find in my GitHub repository, link in the description. We create some arrays, and it's here important to understand the definition of those related to dynamic programming. The most important one is next. Next of IB is the smallest index j that j is reachable from I, and a of j has bit on. What means that for each bit b, we want to know to which suffix of vertices with this bit on we can get. This is the earliest value with this bit on, so in that list, that color, that is reachable from I. And then the recent is something temporary that we'll explain later. We read A, and we go from the end to the beginning, from n-1 to 0. We initialize that next of I bit to n meaning representing position just after the array, so infinity. That is the next value we can visit with this bit on. Then we iterate over edges going from this vertex. We go through bits that are on in this number in A of I, and if this checks whether this bit is on, then we use recent of bit, that is the most recent occurrence of a number with this bit on. So this is the definition of recent. While we iterate from n-1 to 0, most recent position with bit b being on. This is why we initialize that here also as infinity, that is n. Later we'll update that. And if that were, that is next position with this bit on, then we know that we can jump to that vertex, and we want to look to what suffixes of the 19 arrays we can get. And because of that we have a loop from 0 to 18. My next of I b2, I iterate over bits b2, and I minimize that with how can I get from that vertex where to number with such a bit. This minimum is what I explained on the right, taking for each array, if there are two suffixes, I know that, okay, now I can get to the longer one. This is why I take minimum of those two starting positions of suffixes. Plus the bit itself, if I jump from me to another number that has this bit on, then I minimize when I can be in a number with such bit with that position where itself. At the end I update recent of bit, that is the most recent position of a number with this bit on. Then we need to answer queries. Because I numbered everything from 0 to n-1, after reading xy I decrease them by 1. and now in O of 19, O of log, I can answer query. I iterate over all the bits that are on in A of y, that is, I iterate over arrays, those colorful arrays in which A of y is there, actually y, because we store indices there. So where y is, I want to know, can I jump to such suffix, can I reach such suffix that it contains that y inside. And if I find one of those, I mean, if the beginning of that suffix is smaller than y, then I mark awk as true, awk being the answer, yes or true or false, and I can break, because I already found that yes, y is reachable. If yes, if awk, then I print she, that means yes in this problem, and otherwise foo. That's it. If you enjoyed the video, give it a like, and consider also subscribing to my second channel, Errichto 2, where I stream competitive programming and sometimes boring programming streams. So hit subscribe. Thank you, bye bye!